Continuing with the introductory slides today. We have a little bit more slides. I'm going to also show you some movies. There. Can you see?
Sí.
Okay.
Yes, over
Okay. Perfect. Okay. This again, it's not fully part of the course, so it's just an introduction. Okay, so you don't have to take notes or anything. I'm going to give you these slides anyway. And then when we're through with these slides, I have some introductory slides for the thermodynamics part. Again, the first part, again, is still an introduction. So it's about 3 or 4 full classes of introduction, let's say, which you have to follow, of course, but it's not part of the examination or anything. Anyway, we were looking at this slide the other day, which really gives you an idea of how crucially important combustion is. If you look at the numbers, we're always talking about the fact that combustible sources account for at least 90% of the world's energy sources. The rest can be thought of as nuclear or, let's say, renewables, but in these renewables, you also have combustible sources, okay, such as biomasses and things like that. And it's clearly still widely used essentially for its cost. I mean, it is very cheap, okay, to burn things as opposed to do any other thing, okay? Of course, I mean, in the future, there's a lot of work on other sources. In particular, I mean, other than renewables or solar and wind, which are the most established ones, there's also a huge attempt going on in the south of France for the fusion reactor. But that is a long, long time away, okay, I believe. So for the time being, at least for the foreseeable future, we are still going to be having to burn things. And the act of burning, as you know, okay, produces, especially hydrocarbons, produces pollutions. Pollution in terms of, and we'll see what kind of pollution it is, but also CO2, which even if it's the cleanest kind of combustion, CO2 is a product that is really intrinsic within the combustion, okay? It's the destination of the carbon atom, CO2, which is a greenhouse gas and causes global warming, okay? So I'll say 2 things. In the foreseeable future, there is a lot of talk in phasing out the carbon atom from fuels. So namely, burning instead of carbon-based fuels, so hydrocarbons, hydrogen essentially, or blends, okay, mixtures of hydrocarbons and hydrogen. Now, mixing hydrogen with hydrocarbons, well, it's a very hot topic in combustion right now. Some companies are doing this already, trying to see how much hydrogen you can add to your conventional natural gas pipelines. You can't add too much. Hydrogen has the characteristic of being extremely reactive. It has very, very fast flame speed, so it propagates. The hydrogen fires or hydrogen flames propagate very fast. You have things like flashbacks, which essentially, when you try to light something, is a phenomenon whereby the flame will propagate inwards in your device. So that is obviously dangerous. But still, hydrogen does not have CO2 as, or at least you can greatly reduce CO2 as a product of combustion. As you know, if you burn hydrogen and oxygen, you only have water vapor as a product. Okay, this is one thing. The other thing is if you don't use hydrogen, which of course is in its own has its own problems in terms of production. Okay, you can produce it through the electrolysis of water. You can carry it through, for example, other molecules like ammonia. Ammonia NH3 has 3 hydrogen atoms attached to nitrogen. It's an ideal hydrogen carrier. Okay, it's also a fuel to some extent, though it's pretty bad fuel. But if you don't use hydrogen, then you really have to study combustion, in the sense that you have to really know combustion physics in order to understand and mitigate the production of pollution or pollutants. Well, this is another stupid slide here about tomorrow's challenges. Let me see if, well, you're all familiar with this clearly, and you can see how incredibly sort of exponential the growth of the energy demand is really huge. So how do you reduce pollution? How do you reduce the emission of greenhouse gases? Well, you first and foremost need to study combustion. And so combustion for you engineers is not just essentially the conversion of energy within a thermodynamic cycle. That's what you're used to. Okay, so you have, for example, an aeronautical engine which runs on a Brayton-Joule cycle. So your only question is not clearly that of converting chemical energy into heat in order for you to have useful work extracted by the thermodynamic cycle, but it's also the problem of reducing and mitigating pollution. This is because no one is going to let you fly your engine if it's a polluting engine, okay? If it's an engine that produces pollution in excess of the regulated amounts, okay? So there is concentrations of molecules, of polluting molecules that must not be exceeded under international laws, okay? But clearly it's not only that. As you know, in thermodynamic cycles, such as the Brayton-Joule cycle, there's also another upper limit for the temperature, because right after the combustion chamber, you have turbines, okay? And clearly turbines can withstand temperatures maybe in excess of 1,000, 1,200, 1,300 Kelvin, things like that. But after that, it becomes a technological issue, which cannot be, is just more and more difficult to solve. Okay, so these are a little bit the issues. Okay, I would say that in space applications such as rocket engines, well, power generation is clearly very similar in some sense to aeronautical engines. Okay, we're talking about the same kind of thermodynamic cycles. In space applications, things are a little different. We're not going to have time to dwell too much on propulsion systems or actual systems, but the let's say constraints on space propulsion or liquid rocket engines are less stringent. Okay, clearly we're tending to maximize there the temperature, and by temperature we mean a very specific thing, which is called the adiabatic flame temperature, which is essentially the maximum possible temperature achievable, okay, in an isolated system. So a system that fully converts without exchange of heat with the surrounding, converts its chemical energy into heat, okay? So in the stoichiometric proportions of oxidizer and of fuel. Reason being, as you all know, I think by now, is that the maximization of temperature will maximize the specific impulse of your propulsion system, okay? And a great deal of this course will be dedicated to the calculation of both the equilibrium, temperature, and composition. So the adiabatic flame temperature and the equilibrium composition. So that is a very big, very important part of the course. And I'll tell you later. I don't want to tell you too much. So what is pollution? Of course, it's an old problem, yes. We need to have new solutions, and we have, to some extent, a lot of new solutions. But let me just make a list, okay, of the main pollutants that we address as pollutants, okay? So we're talking about products of combustion. So as we know, there is a reaction between a fuel and an oxidizer, and the products of these of this combustion will be molecules that are at a lower energy state, okay, than the fuel and oxidizer, so that essentially we can get heat out of the whole process. This we've seen, but also you can't really choose your own product, okay? It's what you get. So one of the products, for example, is what we call as what we address as soot. Soot is this thing here, the black smoke coming out of the diesel engine. And it's really macroscopic particulates. So when you actually come across things like PM, particulate matter, okay, PM10 or PM5, this addresses essentially solid particles that are macroscopic aggregates of essentially products of combustion, okay, that are of the order of 1 micron, okay, in diameter, or 10 microns in diameter. Essentially, the bad news is that this particular matter, when you breathe it, okay, it really stays in your lungs and cannot be processed by your body. So it's essentially carcinogenic. And needs to be reduced. Now, where does it come from? Well, this is a very specific process that is based on chemical kinetics. So if you remember what I said the other day, if you look back a few slides, when you burn things, you don't just convert directly, for example, methane, CH4, into CO2. As you saw, there are a great number of intermediate steps, which can be very, very complex. And in fact, especially when you have excess fuel, so you have conditions that we call rich conditions. By rich, we mean in excess of fuel, okay? When you have a lot of carbon atoms, these carbon atoms will tend to break up, okay, from the original fuel molecules and reaggregate into even bigger molecules, which is the funny aspect, okay, and the complex aspect of combustion. Not all of the carbon atoms will end up in the CO2 molecule, unfortunately. What happens is that there is, again, in rich conditions, especially in the kinds of flames that we're going to be calling diffusive flames, and I'm going to be talking about those later on, as opposed to premixed flames, we have areas where it is very likely that these carbon atoms will associate into larger molecules. These molecules are called polycyclic aromatic hydrocarbons, and they're essentially kind of ring-shaped chains of carbon atoms with some hydrogens. And they're very likely to stick together to form these macromolecules. These macromolecules eventually will turn into soot, the black smoke. So that's why essentially when you burn things diffusively, so when you have, for example, wood, or you have a fuel that is separate from the oxidizer, okay, you always have a zone, or a candle. A candle is a perfect example. Okay? The candle has, and we're going to talk about the candle later on, it has areas that are very rich in fuel. That's where you get the black smoke, essentially, or the soot. So next time you burn a candle, put a piece of paper on it, don't burn it, and you'll see black soot. That is complex chemical kinetics at work, essentially. Other pollutants, well, sulfur oxides, okay? There could be some sulfur, okay, in your fuel, okay, especially crude oils, refined fossil fuels that can combine with water from the atmosphere to produce sulfuric acid, which is what we call acid rain. This used to be a huge problem, especially in northern countries like Germany or Poland in the 80s, when we're burning huge amounts of coal, for example. Okay. Another quite dangerous pollutant is unburnt hydrocarbons. So some of your fuels, your hydrocarbon fuel, may not fully burn, okay? In your engine, for example, especially inefficient engines like your moped, your motorino, okay? Especially old ones. That's why you need to know about combustion, because modern engines are far cleaner than they used to be. But if maybe someone can remember their father's or mother's little moped in Rome or something that was producing like a bluish smoke, well, that bluish smoke to some extent was a lot of like hydrocarbons that were not being burnt fully. And that's again carcinogenic component of your products. Now, nitrogen oxides, these are incredibly important. Where does the nitrogen come from? Okay, there is no nitrogen, for example, in a hydrocarbon fuel. Well, it's coming from the atmosphere. Okay, so again, if you're burning something, you have to remember that you're not burning it in pure oxygen. That would be called oxycombustion. But you're burning it in an atmosphere which is 79% in volume nitrogen. So nitrogen will essentially give rise to these nitrogen oxides. When you read the X here, is because it could be 1 or 2. Okay, so nitrogen monoxide or nitrogen dioxide, but they're all very, very toxic. Okay. You've probably heard of this in the mitigation of pollutants for aeronautical engines. So again, you have to know about combustion. You have to learn how nitrogen oxides are formed. And usually they're formed at very high temperatures, okay? So that's why essentially low temperature combustion or zones or dilution techniques are used in order to mitigate the formation of nitrogen oxides, okay? You have nitrogen oxides also when you burn hydrogen, okay? As you can see, there is no carbon atom there. So it's a problem also with cleaner fuels, with so-called green fuels, okay? Smog, what we call a smog, is produced when nitrogen oxides reacts with unburned hydrocarbons and ozone in the presence of sunlight, okay? So in extremely polluted cities, you will have smog, like, for example, many cities in China. which is, of course, a massive sociological problem, okay? Now, another pollutant is carbon monoxide. Carbon monoxide, again, is quite poisonous. It's actually lethal. It is essentially colorless, odorless. You don't see it, you don't smell it, but you die from it, okay? Now, CO is really intrinsic in the combustion of hydrocarbons because carbon monoxide is really the very last molecule before carbon is fully oxidized to CO2. So it's just missing one oxygen atom. So CO2 is not toxic, but CO is dramatically toxic. Think about this. So when we're burning things, if for some reason we're not completing, okay, the full oxidation of carbon into carbon dioxide, we're really producing a toxic gas. And this is what happens, for example, when you hear in the news people dying from malfunctioning heating devices, okay? Especially during the night when you're asleep, you don't realize that maybe your heating device is malfunctioning. It's burning inefficiently and not completely oxidizing the fuel into CO2. That's when the device is starting to produce carbon monoxide. So again, very, very toxic, especially in household environments. And then clearly CO2. CO2 is not considered per se a pollutant. It's a greenhouse gas, but again, it has to be considered as, again, a crucial aspect of combustion, okay? In the sense, or what I call here anthropogenic CO2, meaning CO2 produced man-made CO2, because that, as we saw the other day, completely displaces the carbon cycle and essentially extracts carbon atoms from reservoirs back into the atmosphere, where it shouldn't be there. And it cannot be essentially processed naturally and put back into Earth. Some people calculated how many trees we would need to process the CO2, okay, and fix it in an organic solid matrix like wood. And it's a ridiculous number, okay? Hundreds of trillions of trees, something like this. So it is not a viable technique, that of planting trees. It would be essentially a solution, but not one that is practical, really. So what we really need to do is reduce the input of carbon atoms in the atmosphere. Now, let's start playing some videos. You have to tell me whether you see them or not, because probably you can't if I don't share. Can you see this, or can you still see the, or can you do you still see the slide?
No, si vede sempre la slide.
Ok, aspetta. I have to share the whole screen. Okay. Okay, well, what I'm going to show you here is essentially computer models that try to model climate, okay? In order to understand the impact of pollution. So what you can do is essentially have a sophisticated model of the Earth atmosphere where you're really modeling essentially among other things, the radiation from the sun and the effect of a certain concentration of greenhouse gases within the atmosphere. What happens is that through the greenhouse effect, essentially the radiation is being absorbed and then re-emitted at a certain frequency, okay, by the CO2 molecule. Therefore, the end effect is that of trapping heat. Now, there are many models of this kind, maybe 20 around. They're very, very complex computer models that have been developed in a number of years, okay? But the tragic aspect of this is that they all agree. They all agree on the fact that the average temperature is increasing due to the excess CO2 in the atmosphere. So let's see. So this is the National Center for Atmospheric Research. So this is a blend of both computer models and data from satellites. This is a visualization of actual pollution. So this is reality. And it's the ozone that is being produced at the sea level by things like cars and urban centers and factories. So you can actually see, going from day to night, okay, the pulsating input of ozone molecules that are quite visible in the United States. And you can see sort of the dramatic concentration, especially where you're in the populated areas. This is another computer model of the Earth's atmosphere. And essentially, what you have to look here for is the white stuff. The green are carbon from fires, okay? The white is sulfates from fossil fuels and volcanoes. So essentially, you see that burning things has an effect on a global level. In China here, in the US, and in Europe a lot, and in the US, you can see the input of sulfates that is man-made. You should concentrate also on Madagascar here, because there is going to be a volcano eruption. Well, not anymore. I don't know what's going on here. There's going to be a volcano eruption, and you can see essentially, let's say, the natural input of sulfates, which is essentially, I don't know, maybe I missed it. Sorry, blue is the salt water. Well, anyway, if it's not here, then I may have dreamed it, but I remember that there was an eruption, and it was of the same order of magnitude, the input of sulfates. Well, there's some skipping thing. Well, anyway, it doesn't matter. I'll show you maybe another time. But of the same order of magnitude than the daily input of. So it's like having essentially a number of volcanoes, okay, continuously erupting. That's the amount of pollution that we're actually putting into the atmosphere. Now, we'll try to jump from one topic to another here, just to give you an outline of what combustion research is. It's a huge field, okay? So I'm going to give you just a few snapshots, okay, of what's going on. This is one thing that has been going on for the past maybe 30 years or so, which is trying to come up with more efficient ideas in internal combustion engines, okay? I know that lately there's a lot of talk in electrical engines, or electrical power engines, but don't forget that electricity, stored in batteries, ultimately comes from, well, from power plants, okay, which are very likely to run on hydrocarbon fuels. So at the end of the day, when you take two cars, okay, one running with an internal combustion engine and another one running on batteries, at the end of the sort of the life cycle of the car, the pollution, okay, produced by both cars is comparable. This may seem a little off because, of course, electrical engines are far more efficient than internal combustion or thermodynamic engines. But still, taking into consideration the production cycle, the battery cycle, the battery disposal and everything, it is not a complete solution of the problem by any means, okay? By no means it is. So the actual solution would be really to eliminate fuels altogether. Now, let's go back to these ideas. Now, here we have pretty familiar pictures of a diesel piston engine. You see the injector here, and you see these jets. These are jets essentially of fuel being sprayed, okay, into an oxidizing hot environment of air, essentially. This is the typical non-premixed or diffusive flame, okay? By that we mean that there is a fuel and there is air, and they're separate. So what they have to do in order to burn is they first have to mix, okay? The mixing is essentially a diffusive kind of mixing where you have gradients of concentration and mutual diffusion of one into the other, of oxidizer into fuel and fuel into oxidizer. And only when they're mixed, you have an area, a zone, which is this black zone here, which can actually burn. This is a pretty inefficient way of burning things, okay? You really need to create these diffusive zones, these jets. And also, this is what I was telling you about before, you are bound intrinsically, okay? You cannot avoid it, to have areas that are very rich in fuel and that will burn, therefore, with the emission of, as you know, soot, okay? That's why diesel engines are so dirty, okay? And you can't really do anything about it. Because, obviously, this is a characteristic of diffusive burning or diffusive flames. Now, a gasoline engine, on the other hand, works differently. It works through so-called premixed combustion or premixed flames. So in fact, what happens is that before entering the cylinder, okay, the fuel is already mixed. That's why it's called premixed combustion. It's already mixed with the oxidizer. Okay, so what you have here is a nice homogeneous mixture that is flammable. And the way in which these mixtures burn is through the propagation of a flame. Now, you can choose your so-called equivalence ratio. So the mutual amount of fuel and oxidizer, you can choose it. It can be stoichiometric, it can be lean, or it can be rich. So it can be in excess of oxygen or excess of fuel. So for example, in this case, you can totally avoid the production of soot because clearly soot only forms in very rich environments, okay? Here clearly in diesel, because it's diffusive combustion, you're injecting the fuel directly, you have zones where the composition is rich, okay? Now, we know that these two have advantages and disadvantages. So diesel engines, well, they operate at very high pressure, okay? And they have so-called, well, injection systems, and they work on non-premixed combustion, or as it's called, heterogeneous, okay, as opposed to homogeneous combustion. So heterogeneous because you have essentially droplets that are liquid of fuel, and then you have gaseous oxidizing environment. So fuel is sprayed into the environment. So we call this an SCCI engine, a stratified charge compression ignition. What does that mean? It means, well, first of all, the charge of fuel is stratified. Okay, it means that essentially you have different compositions because you have a jet. Okay, you don't have an homogeneous kind of fixed composition. You have a stratified charge. Okay, it changes from point to point, unfortunately. But you have compression ignition. Okay, which, because of the high pressure, okay, thermodynamically it is quite efficient. Okay, so combustion is efficient, and the thermodynamic cycle is efficient. That's why diesel engines were popular. Okay, but the stratified charge is a source of pollution. Okay, so it has good and bad in itself. Now, gasoline engines or spark ignition (SI) use premixed combustion, which we can call homogeneous combustion. So it's just one phase, okay? A homogeneous mixture, a gaseous mixture of fuel and oxidizer. The flame front propagates in a premixed fashion. It burns at lower temperatures. And so we can call this an HCSI engine because it's homogeneous charge. So the charge of fuel is homogeneous, okay? And it's a spark ignition. It's less fuel efficient, okay? But it's also less polluting for the reason I said. So the idea that's been going on for many, many years is whether we can sort of conceive an engine which has the best of both worlds, okay? And this is called an HCCI engine. HCCI means that it's a homogeneous charge, okay, but it's compression ignition. So it's essentially a gasoline engine working in a premixed fashion, but a very, very high pressure, okay? So this combines the advantages of both worlds. So HC is homogeneous charge means that it's less polluting, okay? And compression ignition means that it's high efficiency. So so you see here, the homogeneous charge is ignited everywhere, okay? So essentially there is no high temperature flame, okay? Through this sort of intrinsic or auto ignition, okay? Homogeneous ignitions. So the high pressure now increases the efficiency of the cycle, and this so-called flameless combustion, homogeneous combustion, decreases the emission. So it would be a nice idea, but the thing is, it is extremely difficult to reach and supports in a stable manner this sort of regime of combustion. Okay, so to this day, no HCCI engine has ever been industrially produced, unfortunately. But again, that's why we need to study combustion. Okay. This is another application of combustion research, okay? And it's computer modeling of combustion. Now, this is something that myself, I am involved in for many years. Now, in order to design combustion devices, computational fluid dynamics and computational models are used in an increasing manner, okay? Of course, to carry out simulations, you really need to master the theory of combustion. Why? Well, because essentially this reason. Combustion is essentially, whether it's non-premixed or premixed, always invariably occurs in a turbulent environment. You can see here, okay, especially with Reynolds numbers here associated to both internal combustion engines, or this is a helicopter combustor, but it's an aeronautical combustor. You know, the dimensions, physical dimensions are such that the Reynolds number are extremely large. When the Reynolds number are large, the viscous forces are extremely low with respect to the inertial forces, and you have a turbulent regime where a series of cascading smaller and smaller size eddies are formed, and these will interact with flames. Okay, so that's the whole complexity of the process. Now, in theory, one could say, okay, I can resolve numerically the Navier-Stokes equations, which are essentially the conservation equations for a fluid, okay, or a gas in this case. So the conservation of mass, momentum, and energy. And I can add to this, okay, the transport equations of a number of species that I have in the system that are reacting, okay? So I'll have a source term, which is a reactive source term. I have a bunch of equations, say the combustion of methane involves 50 species, so I'll have 50 extra additional equations. And then I would have to solve them numerically on a mesh, okay, on a numerical mesh. Some of you may be familiar with what I'm talking about here, but clearly these equations must be discretized and turned essentially into equations that can be handled by a computer. So they need to be essentially algebraic in nature. So that's why you need to discretize them on a grid. But this grid needs to have a grid size, okay, which is of the order of the smallest length scale, okay, in your system. Now, what's the smallest length scale in your system? Well, you could say it's the thickness of your premixed flame, for example. You need to have a little few more sort of grid points within to resolve the internal structure of the flame. So we're talking about some, let's say, fraction of a millimeter. By fraction, I mean 100 times less than a millimeter. So of the order of, say, 10 microns, 20 microns, which is also a little bit the scale of the so-called Kolmogorov scale, so the smallest eddies involved in turbulence. Now, consider that this may be a meter in diameter. Well, then the number of cells, grid cells that you need is preposterous. It's far more to this day than you can actually solve on the most powerful parallel high-performance computing system of 2021, okay? Because we're talking about trillions of points, okay? Not just billions. So this approach is called direct numerical simulation, and it is not feasible on industrial size devices. So what we do is we model whatever we don't resolve, okay? So we need larger grid sizes, much larger than your characteristic length scales, much larger, unfortunately, than the thickness of the flame. And then we use models that are physics-based, that is, they take advantage of our knowledge of combustion physics to model whatever we are not seeing on the grid, okay? And this is called, for example, large eddy simulation, which is already, as it is, complicated with non-reacting fluids, but now you have a reacting fluid, so it's much more complicated. Let me show you some examples here. So the first example is an internal combustion engine, okay? So again, you can't see the mesh here, but this is one example. The other example is the one on the right here. You'll see the ignition process of this combustion chamber. So you see a number of injectors here. They're swirled injectors, okay? Very similar to also the ones you find aircraft engines. And in fact, this could be, okay, it's very similar to an aircraft engine. So it's an annular, so you have the shaft in here, and then downstream here, you'll have the turbine, and you have the compressor head. And you'll see that the yellow part is essentially the hot part. You'll see a flame propagating all the way around. Okay? I hope you can see. So you see here the injection, and then you'll see a premix flame forming, you see here, and then propagating all the way down the combustion chamber, you see? Now, this is an LES. So again, there's a lot of modeling here, a lot of subgrid models, okay, that work in order to essentially tell us what is going on within a single cell, okay, which is far bigger than the Kolmogorov scale or the flame thickness. In this particular case, for example, what they did is they thickened the flame artificially in order for you to resolve it. The problem is that you're changing the physics here, so you have to compensate for that, okay? So that's one technique that's being used. Okay, this is another interesting application of computational fluid dynamics in the reactive sense. And so what it is about, this is a scramjet engine. So you may be familiar with ramjet and scramjet engines. Ramjets essentially are engines that don't have compressors and turbines, but they essentially work at high speed, and they compress the fluid just by the action of the ram effect. Okay, the ram effect is essentially a compression in the diffusion part or in the air intake. Clearly, it won't work when the aircraft is stationary, so it needs to be brought to a certain speed, supersonic speed. But in a ramjet, the stream of air is compressed, but it's compressed and slowed to subsonic speeds through a series of shock waves, okay? So that you can burn your mixture, your fuel within this airstream that is subsonic, which is easier to do. Now, clearly at high flight speeds, the losses in terms of total pressure losses through the shock waves are huge. So one way to avoid this and be able to access sort of much higher flight speeds is to carry out the combustion within the engine at supersonic speeds. So this is a supersonic combustion ramjets or scramjet, okay? Now, this is simulation of what's going on in an actual device that's called a high shot. It's just something that is sitting on top of a rocket that was experimented a few years ago, where essentially you'll fly this thing for a few seconds, and within this shell here, which will fly off, you have an air intake, okay? And within this part here, you see the shock here, the shock wave. Within this part here, you'll have combustion, okay? So this is a simulation of a shock wave boundary layer interaction. So you have a turbulent boundary layer here and a shock wave that is stabilized. You see the sort of the lambda shape reflection here, and you see how complex this situation here. We're still talking about large eddy simulations. What you see now here is the injection of fuel in this supersonic stream. So you see a sort of a side or a jet in crossflow, as it's called, being injected within the stream in the hope that clearly you can stabilize a flame of some sort and convert chemical energy into heat. Now, you see pressure here, the pressure field. You see the Schlieren field, which is essentially a measure of the gradient of the of the density, the temperature field, and the velocity field. Okay. Again, very, very complex simulation. It's also quite old at this point, the simulation, but you can only imagine how complex this is. And you can see, for example, the shock waves emanating from the let me show you again, emanating from the jet and cross flow, okay? Now, I'll be honest with you clearly, in order for you to eventually, some of you will be involved in some sort of numerical simulation at some point in your life. Before we can get to this, we need to know what we're talking about. We need to know the physics of combustion. So unfortunately, there's a few steps that we have to take back before we can do this, okay? This is the fun stuff, but we have to do some sort of boring stuff before this. We have to know how to calculate a numerical, thermodynamic equilibrium. We have to know about chemical kinetics. And clearly, we have to know a little bit about reacting flow fields. Reacting flow in general, which can be laminar. In this case, it's turbulent, but before introducing turbulence, you really need to know what the solutions are without turbulence. Okay? So this is one thing. Yeah, but let's proceed a little bit more in detail, and let's talk about the kinds of combustion. Okay, so if you talk about combustion in general, well, the first thing that may come to your mind is, well, a bunch of wood burning like this. It's your typical solid combustion. And this is your typical gaseous combustion. This is both things that we have had some contact with almost every day, right? This is the combustion of in a gaseous form, okay? Now, a combustion scientist will tell you that the wood combustion, which has this yellow color, we'll see why in a second, is your typical non-premixed combustion, okay? What happens here? It's pretty complicated, actually. So when you put a piece of wood in a very hot environment, that's why it's very slow to start, okay, the process. And you need to have a source, localized source of heat. You have a decomposition on the surface, a chemical decomposition, which is called pyrolysis, which essentially decomposes the solid, which is a very long chain hydrocarbon, into combustible gases or fuels. One of those is undoubtedly methane, okay? So we've been talking about methane all the time here. Now, so you need to have heat, you need to have pyrolysis on the surface, and essentially you have an outgassing, a formation of gas blowing into the boundary layer or into the air. Now, clearly, before, as you know now, before it can burn, it needs to mix with the surrounding air. So very much like a diesel engine, you need to have, okay, this mutual mixing or diffusion, actually, of fuel into oxidizer and oxidizer into fuel. That's why essentially you see a flame only in the sort of outer zones of the wood. Okay. Also, now we know we can expect a lot of smoke from this because a lot of black smoke, because being a diffusive combustion, kind of combustion, you will have areas of high concentration of fuel, of carbon. And therefore, that's where you will activate the chemical kinetic pathways that will eventually form polycyclic aromatic hydrocarbons and eventually soot. Now, what about this case here? Well, this is completely different. You see how more sort of elegant and efficient this is? Well, it's a premixed combustion in the sense that you have a supply of natural gas, of gaseous methane, being premixed, okay, with air. So once the gas comes out of the nozzles here is already premixed. So in a very fixed kind of and controlled manner, you will have an output or an outgassing of a premixture of air plus fuel at a certain composition. For example, the stoichiometric composition. Okay. So now we know that combustion will take place in the form of a propagating flame, or as we call it, a combustion wave. Okay. It's nothing to do with acoustic wave, however. It's more of a chemical diffusive kind of process. By diffusion, I mean thermal diffusion. And that will propagate forwards. So it's like a wave, a combustion wave that wants to eat up whatever fuel and oxidizer it encounters in its propagation. The typical flame speeds here are of the order of a few centimeters per second. Okay, maybe 10 or 20 or 30 centimeters per second. So not too fast. Okay. So in some sense, when if you were here, I would make the example of having a gas tank here and opening up. Suppose we want to sort of have a mass suicide here. So we'll just open the gas and we'll wait for the gas to mix completely with the air inside the classroom, and then I'll ignite a lighter. What's going to happen is there is going to be a spherical flame. Okay, it's clearly isotropic. There is no preferential direction, so it has to be a sphere. Okay, moving outwards at about 40, 50 centimeters per second. Okay. So it will take quite a while for the whole thing to burn, but it's going to be pretty fast. Okay. Now, clearly, in a burner like this, it's completely controlled. Okay, so you have a stable flame anchored. Okay, at the side, it's a sort of a Bunsen burner kind of flame. So we'll see how it's stabilized later on. You see this color blue. Okay, completely different. And we'll see why, but there is no yellow. The yellow is a typical color of the carbon atom. So in this particular case, it's also the fact that soot is being heated up, okay, to this sort of bright orange color. Okay, this is the band, the optical band where the emission of carbon occurs. In this case, there is no carbon, you see, emission directly. There is some intermediate species called radicals that will emit on the blue frequency. And these are the CH radicals. We'll see in a while. In fact, let me just, okay. Let me just give you the color thing. I should have put it a little earlier. These are the colors, you see. Chemical reactions produce a lot of atomic species, right? We said that. Intermediate species, CO2, and so on. Now, there are essentially two things that will give out colors, very particular colors. Now, the CH radical that I said before, here it is. You see, so this is a spectrum, okay? A spectral band. So you have you're analyzing the optical emissions in frequency space, okay, in wavelength space. And you see you have a peak at these particular wavelength. If you look at the color here, it's blue color. So CH emits quite intensely in blue color. CH is an intermediate species, okay? It's sort of a species that occurs inside a flame, and essentially in a motion of the flame going into the fuel, it will be a species that will be encountered right in the middle of the flame. Later on, this is going to be oxidized into CO2, okay? But within the flame, it's visible and it will emit in blue color. So that's why in premixed combustion, you have this blue color. Now, the carbon radical C2, on the other hand, will produce in these bands, okay? They're called swan bands. They're far more on the sort of yellow-red side, okay? And this is what you have. This is also why carbon stars are red, okay? And stars as in celestial bodies. And so this is what you essentially have in non-premixed combustion, okay? If you look at this picture here, this is a typical picture of a Bunsen burner. Now, you may be familiar with what a Bunsen burner is because in high school, if you ever had sort of a chemistry lab, it's those burners, okay, that you can adjust with a little wheel, okay? And that wheel is very important, okay? So you have essentially a gas supply of methane, and then you can adjust this wheel to close it completely or to open it. And what this wheel does, it will let air in. If you let air in, it will mix with the fuel to produce essentially a premixed flame, obviously. On the other hand, if you close it, you will only have fuel, so very rich mixture of fuel, that will eventually burn with the air outside. So when you have it closed, this is what happens. I hope you can see it.
I'm sorry, Prof.
Sorry?
Could you make the slide bigger?
Okay.
Because I can't see very well the graph. Thank you very much.
Sorry that, okay. That's as big as it will go. Oops. Oh yeah, I can make it bigger.
Thank you.
So you see here the yellow flame, okay? Now we know that this is burning diffusively. It means that outside of the exhaust here of the outflow of the Bunsen burner, you essentially only have fuel, okay? So this fuel, you see here, it will mix with the outside air, okay, in this particular yellowish flame, which is pretty non-efficient, as you can see, because it will have to wait, okay, for the mixing process, the diffusive process to occur. And in the meantime, in the richer part of the flame, you will have also very sort of dirty combustion with the production of soot, and soot will emit in this particular band or wavelength. Now, suppose you open the wheel now, you let air in, okay, you will have premixed combustion, which is what's going on here, okay? So in this particular case, you have a premixed flame, which is stabilized here with its own speed, okay, wanting to essentially propagate inwards, but because the velocity of the flame, the velocity of the gas, of the combustible mixture is of the same order of magnitude, you have essentially a stabilized flame over here. And it will emit in the blue color because of the CH radical, okay? Now, of course, I did this stupid thing and okay, so that's the idea with colors, okay? Flame colors. Let me go back to this. We talked about diffusive flames and premixed flames. These are the two sort of main ways in which combustion is manifested when you have combustible mixture and you have fuel and oxidizer separated. Now, if you look at a picture like this, here on the right, you may also ask yourself, is this combustion or not? Well, for sure, this is not, right? We know that this will not be combustion. So this is a thermonuclear explosion. We know that in thermonuclear explosions, we don't really have chemical reactions. We have nuclear reactions, right? With a variation, essentially, of atoms species, so elemental composition. So we have atoms or nuclides being changed into something else. In this particular case, into something lighter. In combustion, we know that there is a full conservation of atoms. What you do is you rearrange the atoms into different molecules, which are essentially more stable at a lower energy level so that you can get sort of an excess of heat, but you never have net production or destruction of atoms. You start from your supply of atoms and you have to end with the same number of atoms, the same number of, and the same kind of atoms. So think of combustion or chemical reactions as playing with Lego, okay? You have your Lego pieces to start with. Whatever you do, you'll end up with the same exact Lego pieces, unless, of course, you lose them, okay? In nuclear reactions, you don't, okay? So this is not combustion. Now, where is the energy coming from here? Well, it's coming from the binding energy of the nucleon, okay? So the strong nuclear force binding together the nucleon, okay? When essentially you split an atom, okay, the sum of the two masses will be less than the original rest mass of the nucleon. So the net difference will be output as heat, okay, or in fact as kinetic energy of alpha or gamma rays, okay? The binding energy is huge. Look at this now. I won't even say this number, okay? Millions of megajoules per kilogram, okay, of uranium. So even a very small fraction, okay, or a very small or contained nuclear explosion will yield a huge amount of energy. Now let's look at this thing here. This is an explosion, and I'll tell you that explosions of this kind can be considered themselves as combustion. But why is it combustion? Well, because chemical reactions occur, yes. So there is a rearrangement of the same number of atoms. And the energy stored in molecular bonds will be, well, compared to the binding energy, will be extremely lower, okay? And the difference, the net difference in chemical energy between products and reactants will be output as heat. Now, look at the numbers here. Hydrogen, which essentially has among the highest of the energies per unit kilogram, 140 megajoules compared to this. So orders and orders of magnitude less, okay? Wood has about 15 megajoules, even less. Now, in this particular case, this is an explosive, a TNT, so it's a bomb, okay? A bomb is a very special kind of premixed combustion, which is very, very fast. Now, if you look at the chemical energy per unit kilogram stored in TNT, surprisingly enough, it's a very, very small number. Okay? In this case, 5 megajoules. So what's going on? How can it be that it's actually less energetic than wood? And the trick here is the speed, okay, with which these processes occur. In particular, now I'm going to tell you, the event with which the explosive here reacts, okay, is of the order of some microseconds, okay? So even though the energy stored is very, very small, okay, it will be released in a very short time. So the power associated with this explosion is dramatic, is huge, okay? If you burn wood, the wood will burn in about half an hour. So it will output this amount of energy in a very, very long time. So the power is extremely, extremely small. Associated to this, there will also be shock waves. This is called a detonation, okay? The kind of premixed combustions that we've seen in Bunsen burners however, is called a deflagration. These two things, albeit similar in the sense that they're both premixed kinds of premixed combustion, you need to have a mixture of fuel and oxidizer. The propagating speed are completely different. In detonations, they're several orders of magnitude faster, and they propagate in a completely different way, which involves, again, shock waves. In TNT or in an explosive, why is it a premixed combustion? Well, it is a solid, yes, that's true, but in the solid, you have both the fuel molecule and the oxidizing molecule. They're premixed together in solid state. In some sense, this is similar to solid propellants in solid rocket motors. So in space motors that have solid rocket, solid fuel, for example, the boosters of the space shuttle, or Vega, the European Space Agency launcher, well, you have solid fuel which burns through premixed flames, with premixed combustion. Why is it premixed? Because it's composed of a fuel, of a hydrocarbon matrix. It's called hydroxyl-terminated polybutadiene. It's a very complicated way to just address some sort of solidified polymer, okay? But within it, we disperse, okay, within the solid matrix, a lot of oxidizer, okay? In particular, in those propellants, we use ammonium perchloride, which has a lot of oxygen atoms in it, and also some aluminum powder. You see then that this matrix already comes shipped with whatever it needs to burn by itself, even in a vacuum, because it has both the oxygen molecule and the hydrocarbon molecule. So it will burn through a combustion wave. Now, in the case of the solid fuel, the combustion wave is very, very slow, okay? It will gradually burn in a matter of maybe 2 minutes, okay? A thickness which is about, the order of 1 meter. Now, in the case of an explosive, the detonation, okay, whereas before we had a deflagration, the detonation here in the explosive will propagate in a completely different manner. We're going to study this, which involves a shock wave, okay, and it propagates with speeds in the order of 2,000, 3,000, 4,000 meters per second. So extremely fast. So the conversion of the fuel and oxidizer into products, gaseous products, will be almost instantaneous. In fact, if you look carefully here, you'll see a circular edge here, and this is a shock wave, which is formed because of the immediate expansion of the gases, and it's exactly what ends up killing you, okay, if you're close to the bomb, let's say. So that's not combustion here. This is. Again, this is what the difference is between a deflagration and a detonation. So if you go back to a Bunsen burner, this is what I meant by a Bunsen burner. You have the gaseous supply. Here you have the inflow of air, or the intake of air. And eventually you'll have air and fuel being mixed here. And here you have a flame, which is stabilized in this way. In fact, it ends up picking this particular cone shape because it wants, you see the front here, the premixed front. See, it's very thin, some fraction of a millimeter. Wants to propagate normally to itself. So it will essentially establish this cone shape because the normal component of the flow, okay, of the fresh mixture, will balance the normal velocity of the flame. So depending on how fast you're inflowing here, or supplying the gaseous mixture, if you are increasing the speed, you will have a longer cone like this. And if you're decreasing, you have a shorter cone. If you're decreasing it even more, you may have flashback, okay? And the thing will propagate into the tube itself, okay? So 40 centimeters per second is more or less the sort of a bulk, kind of an average flame propagation speed for hydrocarbons. This is a detonation, completely different, okay? The detonation speed is about 2,000 meters per second. In fact, in solids, it's even more. If it propagates into a solid, you can have detonations in gaseous mixtures or in solids, like bombs, okay? 10,000 meters per second. In fact, the pressures downstream of the flame, whereas here the pressure is more or less constant, surprisingly enough, upstream and downstream. You see here the little molecule, sorry, the little particles that you can use to trace the streamlines here. The pressure is almost equivalent. Here it's not, obviously. And in fact, downstream of the combustion front, you can have pressures that are locally huge. And by huge, I mean 100,000 bars, okay, locally. So extremely, extremely different phenomena, although they're both two manifestations of the same thing, premixed combustion. Let me play you a video which will show you the difference between a deflagration and a detonation. You have to pay a little attention because it's a very short video. So this is a company that is involved in essentially fire safety, okay? So in big chemical plants, this is a very big issue, okay? Because you may have leaks of a combustible mixture. This leak may accumulate in a closed environment and ignite. Now, you want to avoid that the mixture, the combustible mixture, will undergo a detonation, okay? This very sort of dramatic, you can see an example here, form of premixed combustion. You want it, if anything, to burn through a deflagration, a much slower kind of scenario. The fact that one or the other will manifest, well, that's a very difficult question to answer. Usually there's going to be a transition between the two, between a deflagration and a detonation. Now, you'll see this because they can do both in this sort of plastic kind of enclosure here where they will pump in some combustible mixture and they will do both a deflagration and a detonation. So let me just play the video. You can still see okay, right? Because I don't see you guys. I don't see anyone. So
Yes.
Yes,
okay.
Professor.
So what you've just seen here is a deflagration. So I'll just play it again. So it's pretty dramatic, but you can see the flame propagating from right to left. If you are quite careful. So this is a few meters, okay, say probably 10 meters. So it will have a certain speed. Now, bear in mind, these are not laminar speeds. These are more turbulent speeds. So far more, far higher than the standard 40 centimeters per second. So it's a few meters per second. But still, the whole thing will take about a second or so. Now, this is it from a distance. You see that you can actually see the flame front propagating from left to right. So this is from a distance. Again, I'll show you again. Can you also hear the noise? The audio or not? Probably not.
No, l'audio no, il video sì.
No, okay. It's unfortunate because clearly now, when you're going to see the detonation, well, there's obviously a big noise involved because of the shock wave. So let's see now what's going on here. So I don't know if you've seen the amazing difference that you have now between a deflagration. This is a detonation. Look at how fast and how powerful. It's the same kind of energy. It's the same amount, overall amount of energy. It's the same amount of gas, the same gas, okay? But now the conversion happens in a fraction of the time. So the power involved is huge. So it's enough to cause incredible damage, okay? Now you can see it from a distance, and actually you'll be able to see the shock wave. Now you can't hear it, but I can assure you it's very similar to a gunshot. And I'll try to pause it. Now, can you see the shock wave propagating into the grass? So it's very similar to a nuclear explosion in that sense, because it has a shock wave involved, okay? Now, this is, for example, what happened in Fukushima. In Fukushima, the Japanese nuclear plant suffered, as you know, in 2011, a dramatic failure. And one of the things that happened was that there was a huge explosion of hydrogen gas, and it was actually a detonation. So you can actually see, if you go on YouTube, you can see the explosion in Fukushima, which happened to cause most of the problem. It was actually a detonation of hydrogen gas. So you can actually see that. Now, this is the interesting part. So first of all, we know now in premixed combustion that there are these two different modes of propagation. Okay, a deflagration, a very slow kind of useful way of converting species into heat, or chemical energy rather into heat, and then this dramatic sort of detonation, which is a much faster detonation. Now, the first one, the deflagration or premixed flame in general, these are synonyms, propagates slowly, essentially because it's driven by a very slow phenomenon. And this phenomenon is essentially the conduction of heat, or heat diffusion. So as you know, when you try to heat up, for example, a piece of metal in a fire, it doesn't heat instantaneously, right? It will heat quite slowly, because it is involved. It involves the motion, the kinetic energy of molecules that start vibrating. In a gas, this is even less efficient. Okay, so the conduction of heat is the main driving phenomenon. Okay, so it's pretty slow, the whole thing. So what happens is that the reaction zone will heat up fresh mixture. The fresh mixture will reach a temperature that is essentially an ignition temperature. It will start burning. So the whole thing will just propagate forwards. In detonations, the propagation mechanism is completely different. It involves a shock wave, as I said. So there's a shock wave which propagates at the speed of sound, generally speaking, that propagates into the fresh mixture. Now, you may know that clearly the shock wave, what it does, it compresses the gas and heats it up. So now, the mechanism by which the temperature of the mixture is raised is not because it's diffusing heat very slowly, but because instantaneously, very, very rapidly, there is an increase of temperature downstream of the shock. So what happens is that you have a shock wave, the mixture is compressed, is heated up, okay, and enough for it to burn. So now essentially what you have downstream of the shock, you have a combustion process that actually is overdriving the shock. It is actually pushing the shock forward. That's why the whole system of shock wave plus reaction plus combustion moves, okay, at velocities which are far greater than the speed of sound. So it's the shock wave is actually supersonic. It's actually moving much, much faster. Now, whether you have deflagration or detonation is really something that has to do with the conditions, okay? The conditions in which these things are operated, especially in gases. Now, in solids, you can have a detonating energetic material, okay? Like TNT. In gases, it's more probable that you have a transition. And I'll show you here in these last 2 minutes a so-called DDT, or deflagration to detonation transition. So here you see a duct, okay? It's repeated 4 times because it's showing you 4 different things. You have velocity here, temperature, pressure, and heat release. Now, remember if you've done your gas dynamic exam, okay, or some knowledge of gas dynamics. Remember fluids, remember that disturbances of pressure and velocity will travel at the speed of sound. So the first thing you do here, you see this very fast velocity perturbation, which is also reflected in the velocity in a pressure perturbation, which moves very, very fast. Okay, so I'll just play it again. You can see how fast it is. On the other hand, look at this. The temperature here, this indicates the flame. You can probably see a very, very thin here, and this is actually the thickness of the flame, a very thin layer. So this is the very slow propagating deflagration. So this is a premix flame. Now, this premix flame is perturbed by these obstacles. See these obstacles? They've introduced these sort of ridges here in the duct, okay, that perturb the flame, which becomes more and more wrinkled, and eventually it will transition to a detonation. There you go. So you see how you can play it back in the recording when you can play the thing back. There is no in-between kind of propagation speed. It's either propagating as a deflagration or as a detonation. You see? Deflagration, detonation. There is no in-between. So these are the 2 main mechanisms that it has, that the combustible mixture has to propagate. Now, unfortunately, we don't have too much time here. In fact, it's over, but I'll play it back. But when we study these things and we apply the conservation of mass, momentum, and energy, we'll be able to see that the only solutions possible, okay, are these 2 solutions, okay, the deflagrative solutions and the detonating solution, okay? There is no possible sort of in-between kind of scenario, okay? This is a very instructive video because it also enlightens you on how fast disturbances travel in gaseous mixtures, okay? As you know, they all tend to travel through sort of acoustic perturbances at the speed of sound. But then you also have these structures here, which are combustion waves, which you're seeing for the first time probably, okay? Well, okay, so next time I think we have a few slides left, but nothing special. Well, yeah, the candle, I'll show you another couple of movies. The candle is something that we should spend a few minutes on. And then once we finished these slides, I'll start the thermodynamics section, okay? So I'll stop the recording here.